Hey guys, welcome to Ricky by Ken series. In this video, I will take you through heat transfer. Now, heat is a form of energy that travels from one point to the other due to the temperature difference between the 2 points. Imagine that there is a fire here, there is a fire, and then there is an ice at the opposite end. Fire is at a very higher temperature, let's say 1000 degrees Celsius. And then the ice is at a very low temperature, let's say 4 degrees Celsius. Because there is a temperature difference between these two, the heat will flow from the region of higher temperature to the region of what? Lower temperature spontaneously. So heat travels spontaneously from the point of higher temperature all the way to the point of lower temperature. Right? Good. So this implies that the driving force of heat transfer is the temperature difference between them. The driving force of heat transfer is the temperature difference between these two. So if the driving force of heat transfer is the temperature difference between them, then the rate of heat transfer is directly proportional to the what? Temperature difference. The rate of heat transfer is then directly proportional to the changes in temperature between these 2 points. The greater the changes in temperature, then the higher the rate of heat transfer. Okay, let me introduce another term called resistance. Resistance. This is the second term that I'm going to introduce to you today. Resistance simply means the ability of a material to oppose heat flow through it. Every material has its own unique ability to oppose heat transfer through it. Let me give you a typical example. Imagine that you have two bowls in your house. This is plastic bowl in your house, and then the second bowl is what? The second bowl is a silver bowl. Right? This is a silver bowl and this is a plastic bowl. Now, you will notice that when you put the same amount of food in these two bowls, the food in the silver bowl cools down faster than the food in the plastic bowl. The reason is simple. The reason is that these two containers have different thermal resistance. The plastic bowl has a very higher thermal resistance, and because it has a very high thermal resistance, then it will be able to efficiently oppose heat flow through it, and hence it will take very long time before the food inside will cool down. Now, when you consider the silver has a very low thermal resistance. And because it has a very low thermal resistance, it will not be able to oppose heat flow through it. And hence, within a very short time, the food inside will be able to cool down. So this is an everyday life scenario of thermal resistance. Let's talk about the modes of heat transfer. The modes of heat transfer. There are three modes of heat transfer. So these three modes are, we have the conduction. The second one is what? The convection. And the last one is called radiation. These are the three modes of heat transfer. Let me break them down simple for you. So let me break down simply for you. Conduction simply means transfer of heat through solids. The transfer of heat through what? Solid materials. A typical example is that imagine I have a fire here. This is my fire. And I have put a metal rod inside this fire. The heat will flow through this metal rod and I'll be able to feel it in my hand. All right, I'll be able to feel the heat in my palm. And the heat transfer through this is by means of what? Conduction. When heat flows through a solid material, we call it conduction. Now, let me talk about convection. Convection means heat transfer through fluids. So the fluids the fluids can be gas or what? Or liquid. Heat transfer through either of these is by means of convection. Now, let me give you a typical scenario. Imagine that you are boiling water, right? You are boiling your water. This is my water that I am boiling. You will notice that the water molecules close to the surface of the pot becomes warm faster because they make direct contact with the base of the pot. So they will receive the heat. And when they warm up, they become lighter in weight. So they will move up. And then the molecules occupying the upper surface are relatively heavier. So they will rather come down to receive the heat from the bottom. So there will be continuous circulation of the water molecules. So the heat transfer through these fluids is by means of what? Convection. Now let me talk about the last one, which is radiation. Radiation means heat transfer via electromagnetic waves. The transfer of heat through electromagnetic waves is by means of radiation. And a typical example is how heat from the sunlight reaches the earth. Heat from the sunlight comes all the way to the earth by means of radiation. Okay, let's move on to talk about heat conduction or thermal conduction. Thermal conduction and then the calculations associated with it. We will talk about thermal conduction, and there are some calculations that we will have to learn how to do them. Thermal conduction is also called what? Heat conduction. So these terms can be used interchangeably. Now, before I move on to the Fourier's equation, let me teach you how we came by that equation for you to understand. Imagine that there are two people, person A, and then the second person is here, right? And there is boiling water here. There is a boiling water. And there is a direct flame. There is a fire, right? There is a direct flame somewhere here. And these two people are holding the same rod. They are holding what? The same metallic rod. This is the first metal rod. And then this is the second person holding a metal rod, okay? The metal rod are of equal length, they are of equal thickness as well, and they are from the same material, okay? So when you consider these two scenarios, you know that boiling water is around 100 degrees Celsius, but the fire is around maybe 1000 degrees Celsius. The question is, which of these two people will start feeling the burn in his palm faster? The person that will feel the burn faster is obviously the person whose metal is in the fire, because the temperature difference between the person and then the fire is very high, right? The temperature difference between the person here holding the rod in the fire is very high compared to the one whose rod is inside what? The boiling water. So this implies that the rate of heat transfer is directly proportional towards the temperature difference. The greater the temperature difference, the greater the rate of heat transfer. The lower the temperature difference, the lower the rate of heat transfer. As simple as that. Okay? Let me move on to the second scenario. The second scenario is that imagine that these two people, let's say the person one has placed his metal in a fire as well. Let's say both of them are having their rods inside fire, the same fire. But person A is holding a shorter rod. The rod that the first person is holding is what? Relatively shorter compared to that of the second person. So if the rod is short and the person is now standing here, the question is that which of them will start feeling the burn faster? The person who will feel the burn faster is what? The one holding the metal rod that is short compared to the one that is very long. This is because if the length is short, then the heat will be able to transfer through it faster than the one that is broad. This means that the rate of heat transfer is rather inversely proportional towards the distance or like the length of the metal or the rod that you are holding. The longer the rod, the lower the heat transfer rate. And the shorter the rod, the faster the transfer of heat. Okay, so this is the second scenario that I wanted you to take note of. Now, let me talk about the last scenario. Imagine that these two people, the first person and the second person, are both standing at the same place. But the difference is that the rod that the first person is holding is very thick compared to the rod that the second person is what? Holding. Okay, let's say these two people, the first person is holding a thicker rod and the second person is holding a thinner rod. The person holding the thicker rod would be able to feel the heat faster than the person holding the thinner rod. This is because the thicker the cross-sectional area, the more heat will be able to flow through it per second. It's like if the rod is thick, more heat will be able to flow through the rod per each second, and hence the person holding the thicker rod will feel the heat faster than the person holding the thinner rod. So lastly, the rate is directly proportional to what? The cross-sectional area of the rod that you are holding. So these are the three scenarios. Now, after knowing these three scenarios, let's come to the Fourier equation. So Fourier came up with the Fourier's equation by considering all these three scenarios. And he said that the rate of heat transfer, Q here represents heat. Okay, so rate of heat transfer, dq over dt, which is the rate of heat transfer, is therefore directly proportional to what? Changes in temperature. It is also proportional to what? The area, but rather inversely proportional to what? The dx. So dq dt is directly proportional to a dt. Let me use dt. Okay, a dt over dx. It is just a combination of these three scenarios. Just a combination. So dq dt is proportional towards a dt dx. Good. Now let me talk about something. We are going to remove the proportionality sign here and then introduce a constant. So dq over what? dt would then be equal to constant k dt over what? dx, where the constant k is called thermal conductivity. Thermal what? K is what? Thermal conductivity. Thermal conductivity is simple. The ability, or like it just has to do with the rate at which a particular material transfers heat. Or like yeah, the ability of a particular material to transfer heat has to do with its thermal conductivity. So let's say I have a copper rod, and let's say I have an iron rod. These two are of different materials. So because these are different materials, they will then possess different thermal conductivities. But it remains constant no matter the length of the rod or the thickness of the rod. They will always have the same thermal conductivity since they are made from the same substance. So this is the Fourier's equation. So at a steady state whereby changes in temperature is constant, then the dq over dt will tend to be small q. So you can see this equation in several textbooks. Q is equal to what? K dt over what? Dx. Q is equal to K dt. Sorry, I forgot the A. Ka dt over dx. Ka dt over dx. This is the Fourier's equation. So take good note of the equation, and it's not about memorizing. Just know how we came by this equation so that always when you're doing the calculation, you will understand whatever you are doing. K is equal to what? Ka dt over dx, where K here is what? The thermal conductivity, A is the cross-sectional area, dt is the changes in temperature, and then the dx is the length of the material that you are working with. Now let's consider this worked example to test our understanding. A cork slab 10 centimeters thick has one face at minus 12 degrees Celsius and the other face at 21 degrees Celsius. If the mean thermal conductivity of cork in this temperature range is 0.042 joule per meter per second degree Celsius, what is the rate of heat transfer through 1 meter square of wall? Let's say I have a cork slab. This is my cork slab, and one face is at 21 degrees Celsius, and then the other face is at what? Negative 12 degrees Celsius. And then the thickness of this rod is given as what? The thickness is 10 centimeters thickness. Okay, and we are given the thermal conductivity, which is what? The K, to be 0.042 joule per meter per second degrees Celsius. This is the thermal conductivity. And we are given the area to be 1 meter squared. And we are asked to calculate the rate of heat transfer through 1 meter square wall. Now, this is very simple. Let's use the Fourier's equation. The Fourier's equation says that Q is equal to Ka dt over dx, right? We know K, we know our K, we know our A, and then the dx or the x is given as 10 centimeters, but we need to convert it to meters. So 10 centimeters to meters will be what? 0.1 meters. And let's consider the temperature difference. This is 21 and then this is minus 12. So the temperature difference will be equal to what? 21 minus negative 12. And this will give us 33 degrees Celsius. So let's fix everything into the Fourier's equation. So our rate of heat transfer Q would be equal to K, which is 0.042 times our area, which is 1, times changes in temperature, which is 33, over the thickness, which is 0.1 meters. And at the end, we will have the final answer to be 13.9 joule per second. So this will be our final answer. Let me give you another word example. Solve this question, and when you finish, comment with your answer and I will respond to you. Thank you very much for watching this video. Stay tuned for more videos on heat transfer theory.